Hello, my name is Daniel ten Wolde. I am a PhD student at the CWI Database Architectures Group, and together with Gabor Tsanias and Peter Bonks, I'll be presenting DuckPGQ, bringing SQL-PGQ to DuckDB at the VLDB 2023 demonstration track in Vancouver. The goal of the demonstration is to introduce the new SQL property graph queries or SQL-PGQ syntax. We want to show DuckDB and the DuckPGQ extension in particular, which can handle this new syntax. We will allow users to interact and write their own queries. And we want to show how these queries are translated into relational query plans. So SQL-PGQ is mostly related to graph data management, to graphs. And when we talk about graphs, we have our nodes, we have our edges. We talk about highly connected data often with many-to-many relationships. And in particular, we are talking about the property graph model, where every node and edge can have a label, and node and edges can have properties. And this can already be presented as tables in a relational system, where the columns are the properties, and the label can be the table name. So then we want to do graph exploration. And in this case, we define graph exploration as pattern matching, where we want to find sub-patterns in our graph. Or we want to do path findings, finding the shortest path between two nodes, for example. And we still want to do aggregations and filters and normal relational operators we are familiar with. So for the demonstration, we will be using the LDBC social network benchmark dataset. This is emulates a realistic social network with realistic properties. So for example, the most important one is persons who can know each other. Persons can post a message on forums, and persons can work at or study at a company or university, and they live in a city, etc. So this dataset will be available to the user, to the audience, in various scale factors, so they can interact with it and see how it works. So now I want to introduce SQL Property Graph Queries or SQL-PGQ. It is part of the official SQL 2023 standard, and it was released in June of this year. In SQL-PGQ, we define graph tables over already existing tables. So this is sort of like a view over your already existing data. It introduces read-only operations for graph queries, and in particular, more precise syntax for path finding, easier to understand, and for pattern matching. We'll see examples in a bit. So for these graph tables, we make our distinction between the vertex tables and between the edge tables. So the vertex tables, we list them here, where we reference first the table, the existing table name. Then we have an optional properties list, which can be the columns that we want to use in our SQL-PGQ queries. Then we can exclude a couple of columns if we want to. And then we define the label, which we'll be using to reference this table. And this label does not need to be the same as the table name. And then there's this indiscriminator, which is going to be a special column if you want to do inheritance. I won't be going into too much detail, but during the demonstration, we can show this. Then for the edge tables, it's fairly similar. We still have the properties and we can exclude columns. We can do inheritance. But now we also need to define the source key and the destination key for this table. So this uses a foreign key, primary key relationship. So the source key is a foreign key and then references a primary key in another table. An example of creating a property graph called SMB in this case, where we define the vertex tables, person, and forum. And this is a subset of the property graph I showed earlier. And then the edge table, person knows person, where the person ID references the person table, and the destination key also references the person. And then there's forum, which can have members. So self-explanatory. We start from a forum ID, and the destination is a person ID in the person table. So we have a couple of example queries. This one, for example, the interactive complex query 2 from the SMB. Where we start, we are given a person ID, a person node, following a nose edge, and this is an undirected edge, to a friend, who is the creator of a message with a maximum date. So the SQL PGQ query for this would look as follows. We introduced this new from graph table stand keyword, where we reference the property graph that we defined earlier. And then we have a match statement where we start our pattern matching. In this case, we start from person, which we give an alias A, where we filter on the person ID. And note the round brackets, which means that we're talking about a vertex in this case. Then we go to a nose edge and note the dashes on both sides of the nose edge, where just 2 dashes means it's an undirected edge that can be left directed, as you see later, and it can also be right directed. So there's a couple of variations defined in the standard. Then we can use the columns to note which tables we want or which columns we want to return. And this ties in pretty nicely with the friendlier SQL with DuckDB, where we don't have to start in DuckDB with a select statement or select, but we can omit this, which is interpreted as a select star. And then we can, outside of this graph table, we can do an ordering, we can do additional filters, we can do aggregations, etc. Another example is interactive complex query 13, where we are given a person 1 ID, we're given a person 2 ID. And then, again, an undirected edge, but a nose with 0 to an unbounded amount of hops in between. So these persons don't need to be directly connected. There can be 0 hop in between, there can be undefined many in between them. In SQL PGQ, this would be the following, or this could be implemented as the following, where we want to find the shortest, any shortest path in between these two. And note the cleany star here after the nose edge, which means there can be 0 or more hops in between these two. We store the path as a path variable p in this case, and in the columns class we can say we want to return the path length of p. We can also return the path itself. This is as a list. So then we can know which edges and which nodes are in between these two persons. So we saw an example of the cleany star, which means 0 to many hops. But there can also be a defined lower bound or a defined upper bound. And there's also cleany plus, which says from at least 1 hop to an unbounded amount of hops. And there's the question mark, which means 0 or 1 hop in between. This is a special case which is not yet handled in DuckPGQ, but will be in future iterations. So the relational query plan for 13, well, part of it looks like this. We don't introduce any new operators. Instead, we create a compressed sparse row data structure using parallel use-defined functions to create a compressed sparse row over which we can do efficient pathfinding algorithms such as BFS or Bellman-Ford if we need to do cheapest path. We implemented this in the open source in-process analytical database system DuckDB, which by now has 12,000 GitHub stars and over 2 million downloads in the last month. It was originally developed at CWI by Hannes Mühleisen and Mark Raasveld, and it uses a vectorized execution engine, morsel-driven parallelism, and as I said earlier, it supports scalar use-defined functions. And important for us, they allow extension modules similar to Postgres. So the main code base of DuckDB will stay small, and the users can install and load extensions pretty easily by on demand. So if you want, for example, time zones, there's an extension for that. If you want to use geospatial data, there's an extension. And now also for SQL PGQ, which is DuckPGQ, where we have a parser, which is a SQL parser plus the PGQ syntax. So it's a superset. And we use this using the parser extension of DuckDB, which kicks in as soon as a query cannot be parsed by DuckDB itself. It will go to this parser extension, and then we can parse it and handle the query. We translate all queries to standard relational query plans, so we don't introduce new operators. And for pathfinding, we do on-the-fly compressed parse row creation, and then we do SIMD-friendly multi-source breadth-first search, where we make use of the vectorized execution model to do efficient pathfinding. Installing the extension is as simple as loading up a DuckDB shell, then running install DuckPGQ and then load DuckPGQ, and then you can start to write your SQL PGQ queries. So to conclude, in this demonstration, we introduced the SQL PGQ syntax. We showed the DuckPGQ extension where we only translate to relational query plans, don't introduce new operators. And we do efficient pathfinding using compressed parse row creation and multi-source breadth-first search. If you want more information, the QR code on the left will take you to the DuckPGQ extension on GitHub. It's all open source, and if you use it, find a bug, you can create an issue. If you want more information on DuckPGQ, DuckDB, LDBC, or SQL PGQ, you can follow the QR code on the right, which leads you to a slide deck with even more features that I didn't cover about SQL PGQ and etc. Thank you very much for watching.